Hello everyone, and welcome to presentation on the challenges and opportunities of Vitrimers for aerospace applications, a roadmap for sustainable and high-performance materials. Today, we will explore how a revolutionary class of polymer networks is paving a transformative path for next-generation aviation and space structures. In this sector, reliability and endurance are absolute. While traditional materials have pushed the limits of efficiency, we have reached a critical bottleneck where sustainability and advanced mechanics must coexist. Over the next few minutes, we will examine how Vitrimers bridge this fundamental gap, diving into their molecular behavior, manufacturing challenges, and future industrial implementation. Let us begin by analyzing the rigorous demands placed on aerospace materials. The modern aerospace industry operates under a continuous engineering paradox: the need for structures that are exceptionally strong, thermally stable, and ultra-lightweight, while simultaneously adhering to strict sustainability goals. Components such as fuselage skins, wing spars, and interior structures are subjected to hostile operational conditions. These include heavy dynamic mechanical loads, aggressive vibrations, cyclic fatigue, and severe chemical exposure to aviation fuels and hydraulic fluids. Historically, high-performance thermosets, like epoxies and bismolimides, have been the gold standard due to their rigid, permanently cross-linked networks. However, these traditional materials are inherently flawed. Their permanent networks make them brittle, susceptible to microcracking, completely incapable of self-healing, and virtually impossible to recycle, leading to substantial economic and environmental waste. To overcome these historical limitations, material scientists have turned their attention to a groundbreaking subgroup of polymers known as Vitrimers. Vitrimers belong to a broader classification called covalent adaptive networks, or CANs, featuring intrinsic, dynamic, covalent bonds. What sets Vitrimers apart from any traditional polymer is their unique associative bond exchange mechanism. In conventional thermosets, chemical bonds are locked permanently. In thermoplastics, bonds dissociate completely when heated, causing a sharp drop in structural integrity. Vitrimers, however, operate on a principle where new covalent bonds are created simultaneously before old ones break. This ensures that the overall crosslink density remains completely constant throughout the chemical exchange process. Consequently, this unique chemistry effectively bridges the gap in polymer science, providing thermoset-like mechanical stability under operational conditions alongside thermoplastic-like reprocessability and flow when thermal energy is applied. Let's transition into the mechanical integrity and structural challenges associated with these adaptive materials. Structural aerospace applications demand superior resistance to cyclic stress and impact loads to prevent premature fatigue failure. While Vitrimers offer highly tailorable mechanical properties, allowing engineers to adjust stiffness and toughness by manipulating crosslink density and bond exchange kinetics, they introduce a critical engineering hurdle: creep and stress relaxation. Because the covalent bonds within Vitrimers are dynamic, long-term exposure to sustained mechanical loading, especially under stress, can trigger progressive molecular rearrangements. This causes the material to deform over time. For primary load-bearing structures in aviation, even a minute amount of structural deformation is unacceptable, making creep resistance one of the primary challenges that researchers must resolve. Moving on to thermal and environmental thresholds. As established in recent literature, aerospace composites must endure extreme temperature fluctuations. This ranges from the freezing cold of approximately -50 degrees Celsius at cruising altitudes in the stratosphere, up to over 200 degrees Celsius near engine components and localized friction zones. Currently, the thermal and oxidative resistance of most Vitrimer systems does not yet surpass that of conventional, high-performance aerospace polyimides. Furthermore, exposure to moisture, ultraviolet radiation, and corrosive aviation fluids can accelerate matrix degradation, therefore developing molecular architectures with higher glass transition temperatures. While integrating robust protection strategies like UV stabilizers and antioxidant additives is essential to guarantee long-term survival in harsh operational environments. Despite these challenges, the true commercial appeal of Vitrimers lies in their capacity for self-healing and their contribution to a circular economy. The dynamic nature of their covalent bonds enables the autonomous healing of microcracks. When an aircraft skin experiences microdamage due to fatigue, localized thermal activation triggers bond exchange across the fractured interface, effectively healing the crack and extending the operational lifespan of the component. Furthermore, Vitrimers offer a viable path toward a circular economy. They support both mechanical recycling through reshaping and chemical recycling through targeted solvolysis. This introduces a genuine cradle-to-cradle life cycle, drastically reducing material waste, lowering the carbon footprint of components, and minimizing life cycle energy consumption compared to conventional, single-use thermoset composites. Now, let us examine manufacturing compatibility. starting with liquid molding techniques like resin transfer molding and vacuum-assisted resin infusion molding. While Vitrimers are highly promising, integrating them into traditional aerospace manufacturing lines poses major processing difficulties. The first issue is high viscosity. The dynamic network structure often exhibits a higher intrinsic viscosity at standard processing temperatures, which severely hinders the thorough impregnation of reinforcing fiber beds, potentially leading to internal voids and structural defects. The second issue lies in curing kinetics. Vitrimers typically experience earlier gelation points compared to conventional epoxies. This narrow processing window requires highly precise temperature and pressure management during the resin infusion stage to ensure complete saturation before the network locks into place. Beyond liquid molding, we must evaluate modern advanced manufacturing methods, specifically automated fiber placement, or AFP, and additive manufacturing. Automated fiber placement is crucial for scaling large aerospace structures, but it demands strict control over resin flow and tackiness. If the Vitrimer matrix relaxes too quickly or flows unpredictably during the continuous deposition of carbon fibers, it can introduce geometric defects, such as gaps, overlaps, or fiber waviness. On the other hand, additive manufacturing, such as 3D and 4D printing, opens up incredible opportunities for fabricating complex aerospace geometries with minimal material waste. However, successful printing requires an exceptionally precise thermal window. The temperature must be high enough to allow rapid bond exchange across the printed layers to ensure strong interlayer adhesion, but low enough to maintain structural stability during deposition. This brings us to the core science of managing these materials, tailoring bond exchange kinetics. The macroscopic performance of an aerospace Vitrimer relies entirely on the delicate balance between segmental dynamics and bond exchange time. As defined by the Arrhenius model, the stress relaxation time follows a strict temperature dependence governed by activation energy. By strategically selecting catalysts and designing specific molecular architectures, we can precisely control the activation energy required for bond exchange. Our ultimate engineering goal is to design a Vitrimer system that remains completely rigid, stable, and resistant to stress relaxation under normal, high vibration flight conditions, yet becomes highly dynamic, flexible, and reprocessable when heated to a specific threshold during ground-based maintenance and repair operations. Furthermore, Vitrimers open the door to advanced, multifunctional aerospace composites that go beyond simple structural support. For instance, by integrating conductive nanofillers like carbon nanotubes into the Vitrimer matrix, we can achieve structural health monitoring. This allows for real-time sensing of internal damage via electrical resistance changes, and it can also enable joule heating to trigger localized self-healing or de-icing. Additionally, shape memory Vitrimers can be engineered to create smart morphing structures, allowing aircraft wings to adapt their aerodynamic configurations dynamically during different phases of flight. Finally, intrinsic flame retardancy is being actively developed to ensure these advanced systems comply with the ultra-strict safety and fire standards mandated for aircraft interiors and engine bays. However, navigating this vast molecular design space using conventional methods is incredibly slow. That is why researchers are accelerating discovery through artificial intelligence and machine learning. Traditional trial and error experimental pathways are time-consuming and resource-intensive, often taking years to optimize a single resin formulation. Machine learning models can break this bottleneck by effectively predicting structured property relationships. By training algorithms on existing chemical data, AI can accurately predict crucial aerospace metrics, such as the glass transition temperature, creep resistance, and self-healing efficiency of hypothetical Vitrimer formulations. This enables targeted synthesis, allowing scientists to bypass thousands of unsuccessful formulations and rapidly discover optimal candidates tailored for specific aerospace components. In conclusion, let's look at the roadmap to industrial adoption. Despite the extraordinary scientific breakthroughs achieved in laboratories, a critical gap remains before commercial aviation implementation can occur. The primary roadblock is standardization. There is currently a severe lack of official industry standards from regulatory bodies like ASTM, FAA, and SAE, specifically governing dynamic covalent networks. To bridge this gap, extensive, long-term comparative studies under real-world operational stressors such as radiation, cyclic loading, and chemical aging are absolutely imperative. Ultimately, as we overcome these processing and regulatory hurdles, Vitrimers will undoubtedly redefine the next generation of resilient, sustainable aviation and space materials. Thank you for your time.